Hello everyone, welcome to this talk. My name is Katrien van Landeghem. I lecture marine geology at the School of Ocean Sciences at Bangor University. I'm very pleased today to be talking about monitoring the retreat of glaciers using sound waves. So first of all, I'll tell you why I'm so interested. I need to convince you that you should be interested, and how we do use those sound waves. And I'll be talking about glaciers from the past, the paleo glaciers, and I'll be talking about the glaciers of the present in our polar regions. And somehow Trump makes an appearance. So, why would we want to know about glacier retreat? And I'm talking here about the marine terminating ones, because the marine terminating glaciers will actually be influenced by the ocean body, and that ocean body is warming. And that's the whole point, actually. That's the whole rationale. What is happening here? And where you can find that information is in the IPCC reports, because this is the Intergovernmental Panel on Climate Change that will deliver, or that is delivering via a report every few years, some really objective scientific information, because we need to know the risk. We need to understand the risks of the climate crisis that we are indeed inducing ourselves. We need to know what the impacts are, and we need to know what the response options would be. And so the IPCC report, and I put a link in here to that report, really details that very, very clearly. It is a lot of pages to go through. And so I also refer to the infographics that were made by Energy and Climate, and I provide a link to those here. And those are also the infographics I'm using in this slide. Because as you know, 71% of our Earth's surface is actually covered by oceans. And we've seen that since the 1970s, that all that excess heat, that additional heat that is caused by humans, the global warming really, all that heat has been, or 90% of that heat has been absorbed by the oceans since 1970. And so global warming really means ocean warming. And we have indeed seen that the rate of that ocean warming has been more than doubled since 1993. So we are facing a very big problem here, because these are the consequences. We have globally sea level rising, and so at the moment it's been about 3.6 millimeters per year since 1993, but you'll have seen recent reports indeed that worst case scenario model that appeared in the IPCC report is indeed the kind of sea level rise that we see at the moment. So things are not improving at all. Okay. So what is contributing to the sea level rise? Well, it's indeed the warming of the oceans itself, because as you have a warmer body of water, you have an expanding body of water, and it can only go one way, and that is upwards in a way in that ocean basin. And so you'll end up having sea level rise. But the biggest contributors, and that is my rationale of my talk, is actually the melting of ice sheets and of glaciers. And that is the dominant source of sea level rise. So we really need to investigate when and how and why that happens. Okay. That reason really is that we need to be concerned for the people living close to the coast, because it causes the sea level rise is causing flooding, in particular in areas that are low lying, of course, and a lot of those areas do not have the means to react to this appropriately. And for instance, in Bangladesh alone, you would see 18 million people displaced if nothing actually has been done by 2050, and the sea level rise continues as it is, and it's quite likely that it would do. And recent media coverage actually has also focused on those retreating glaciers, because things are looking pretty bleak in our polar regions indeed. And the middle video I will actually refer to in this talk as well, and I'll give you the link to that because that's linked to our own project. So we have a problem that we see that there's a rapid retreat of the present day ice sheets. Now, we know that climate drives this, the ocean warming because of the global warming, but there are also local drivers. So the ice dynamics themselves, but also locally, what are the environmental parameters? What's the geography of the area? And so it's quite a complex picture. And so we need to understand when and how that glacier retreat is actually quicker than expected. Okay. Because of course it's the moving parts of an ice sheet, like an ice stream and a glacier, that ends up draining a large ice sheet. So we need to know how those ice streams and those glaciers are regulating the stability really of this ice sheet, and that is really quite important. Now, not always do we have the luxury, of course, of looking at polar ice caps because we don't always know what's underneath because there's kilometers and kilometers of ice on top of that bed. So what can we do? We can actually look at the paleo record. And about 25,000 years ago, we had a British and Irish ice sheet over the top of us. Well, not quite over the top of you, but we did have them over the top of where we are in Bangor, okay? And over other large parts of Britain and the Republic of Ireland. So the Irish Sea ice stream was one of those conduits actually that would drain, in fact, it was 15% that would drain that former British and Irish ice sheet, and that was a marine terminating. Yeah. So it's actually a really good analogy of how things might happen at the moment in the polar regions, and that's why we investigate that. So we want to know, how did this ice stream in the past, how did it change direction? How did it change its speed? And why? Because we might learn something about the present. And then with sound waves, you think, if you remember the title, are we shouting aggressively at the ice front? No, we are not. We are, well, we are actually, but we're not using our voice. We're using an instrument that is mounted at the bottom of a vessel. This is a multi-beam echo sounder, and with a fan of sound, you can then you can record the time it takes for all those sound waves to come back at you. So it pings off the seabed and it comes back at you, and you're able to actually form a three-dimensional picture of the landscape of your sea floor. Very much like you have your landscape here on land, the terrestrial one, you have one underneath all that water. Yeah, so that we can now document using sound waves. Why would you want to do that? Well, when ice goes over a bed, it actually changes that landscape or that seascape or that seabed, and it makes bed forms. And those bed forms are indicative of the way it paints a picture of the way that the ice was going over that bed. So, for instance, the rib moraines, they would be quite indicative of very slow ice speeds, and in fact, the bed was frozen. We know that from other people's research. Drumlins, they're like teardrop-shaped bed forms. They would be in line with the ice flow direction, whilst rib moraines were perpendicular to them. These are in line with ice flow direction, and a bit faster the ice flow would be to generate those. If you see megascale glacial lineation, that's panel C here, that means it was fast ice flow, very erosive, very long bed forms are actually formed, again, in the direction of that ice flow. There are other glacial bed forms that are very indicative of an ice flow, but these are the main ones, and we found them in some records that I will show you now. And again, using sound waves, we have therefore been able to investigate paleo ice stream retreat. I shall give you an example. So this is my location map, and you can see here, this is the Irish Sea. I hope you recognize that, between Ireland and Great Britain. And between the Isle of Man and Anglesey, you have this black outline, right? And that is the outline of our entire data set of this multi-beam echo sounder data that paints a picture, a 3D picture of the sea floor topography. In red, in this box here, you see part of that data set, and then another small part of that data set in this black outline. That's what you see in this entire slide, okay? So the seabed here is between 28 and 91 meters deep, the blue being the deepest and the red being the shallowest. So I see immediately this is not a boring flat seabed. It has a lot of bed forms on it. Indeed, I see, broken up, but still quite clearly, these very long megascale glacial lineations. Here in the eastern side, I see rib moraines. Not so clear here, but maybe if I zoom in, broken up again, but clearly rib moraines. If you look at them quite frequently, you do start recognizing them. A bit further up here to the west, you see drumlins. And I'll zoom in again. These teardrop shapes, I hope you recognize. And also these really thin, kind of long bed forms. And we call them flutes. They actually overprint them. Yeah. Then we have some push moraines here in a bit of a belt around here, like all little ribbles, really. And what we also have are iceberg pits, and they are left by an iceberg carving off the ice margin that sits on that bed. And as it carves off, it actually just slumps onto the bed, and it leaves with its keel mark a pit or a drag mark on the seabed. And really, still today, 25 years after this has happened, or in this area is actually 20,000 years, it is still visible because it's perfectly preserved it. Nothing's covered it, it hasn't been eroded since. So a beautifully preserved paleo landscape here on the bed of the Irish Sea, just to the north of Anglesey. And so all these pits are all drag marks of those icebergs carving off dramatically right before the ice went away. So now I can kind of reconstruct what happens because I read a lot about this. MSGLs, it must have been fast ice flow, very erosive. Fluted rib moraines, ice flow, but initially from a frozen bed. Then the drumlins and the flutes, ice flow, but with a thawed bed. So it's all very deformable because it's no longer frozen. And then the push moraines is actually indicative of retreating ice margins and constantly pushing some sediment in front, but it eventually goes away. And of course, all the iceberg pit marks would give us that evidence as well. The ice eventually retreats away from this area. So chronologically, I have first ice advance, very erosive. And what we also see is that it left the bedrock exposed. It's more sticky. That's important because that stickiness allowed freezing to happen. And this is where the rib moraines indeed tell us that. Then you have on stream of drumlins again. But what happens here, there's an ice flow realignment, yes, because of this exposure of the bedrock, because of the bed changing, yes, it becomes more sticky, yeah, and it slows the ice down and allows spatial freezing between the ice and the bed. And then there is faster and thinner ice, again in a slightly different direction, with an intense carving, and that's kind of the last act of the ice before it retreats entirely. So this erosive initial ice streaming actually determined what happened afterwards, because it left that bedrock exposed, it made it stickier, it made the bed freeze and therefore realign that ice flow. So that's what we know now from the paleo environment. Now, what do we do in the present day environment? Well, first we take a plane from the Irish Sea environment to Antarctica. Plane number 1 to the Canaries, plane number 2 to Falkland Islands, and then a vessel through the Drake Passage. Terrible. It's like being in a washing machine for 5 days. So it's not easy peasy lemon squeezy at all. But then you finally get there, West Antarctic Peninsula, absolutely beautiful. And then I could just show you so many pictures. It is the most mesmerizing environment you could imagine. Icebergs, penguins, whales. It's really great. We come out into the West Antarctic Peninsula, which is actually not that far away, and I show you from one fjord what we've seen. So this is the William Glacier by Borgum Bay near Anvers Island, which is Antwerp Island, and that looks like that. So when you actually steam into this fjord, again, mesmerizingly beautiful. And please do click on this video or copy this link, because this is what happened there. The ice was actually carving as we were there, right? So we know it's a very dynamic environment. And so what we were there to do is to collect all the data that will help us understand why there is such variation. Because in a nutshell, between the 3 fjords that we went to visit in 2017, 2018, and 2019, we see there is a difference and how this ice is retreating. We also see that these are the glacier fronts since the 1950s. Every fjord has its own history as well and how that retreat has happened. And so what we have done is we collected evidence of this seabed again. So I hope you recognize in the meantime, this is seabed bathymetry data now in the colored range. And we took samples in the transect towards the ice front. Of course, the ice front is here. Yeah. And what we want to know was 2 things really. Why are there such variations in ice margin retreat and sometimes even advance? Why is it not only different between the fjords, but why is it different along one fjord ice margin? And why is it different from year to year? Because that is also what we've seen. What we also want to know is what the impact is of all of this on the seabed and on the biology that lives there. Yeah, and that's why we've taken all those samples. And then there was a lovely surprise thanks to our brave captains, because we've also been able to use our fan of sound to look at the actual ice margin itself. And you can see a little bit of it, of course, peeking over the top of the sea surface. But we also want to know what's underneath that sea surface. And this is what we were able to capture. So you see here in a point cloud, what the actual shape of that ice margin is. Because you have the ice, the glacier, sitting on the bed of the sea bed, or and we actually see that transition perfectly because of these sound waves. So we can learn from that. Here, for instance, is an example of what we've seen in another fjord, and we see this undercutting, and we need to understand why there is such an undercut. And that is what we're doing in this project. We are actually trying to get grips with these variations between the fjords. Why? Why is the ice front morphology different? Why is the retreat rate different? Why is the seabed in front of the ice front different? And so why is there such variation? And of course, it has to do with a lot of things like the fjord morphology and the geology and the seabed changes and the erosion of that seabed. And of course, I hope that rings a bell because that's something that I introduced at the start of the presentation, that from the paleo environment, we know that a reduction in the deformable bed will influence an ice stream. So we're looking to use that knowledge to now better understand what happens in Antarctica. So very much still work in progress, okay? So preliminary, we are bringing all this data together, oceanographic data, geological data, glacial data, to try and disentangle these things. So keep an eye on it. We will be publishing on this soon. But as a small summary, we use the sound waves to actually remotely observe how a glacier retreats. We've looked at it in the paleo environment, the glaciers from the past, and we're looking at it from the glaciers in the present day in our polar regions. Okay, so we use that fan of sound to not only look at the seabed itself, as you can see here in the background as well, but also the morphology, the shape of the actual ice margin itself and how it meets the bed. I've added some of the mostly free of charge accessible papers. The one that isn't, in fact, is my own here from 2020. If you're interested, just ping me an email and I'm happy to share. And I thank you very much for listening. This is just a picture of some sea ice we never ended up going through and had to just escape out of there. But I think the seals had lots of fun looking at us struggling through it. And any questions, please, I'm happy to answer.